Sir, recording also, sir.
Okay.
Okay. Yeah. So let's start with the paper. Okay. So consider three weight vectors. So basically you have three models. Okay, first I'll read the question. Consider that the three weight vectors W1, W2 are learned and W3 are learned from six-dimensional data set using a linear regression model or regularized versions of linear regression model, not in any particular order. So these are the three models, okay, corresponding to different linear regression, okay, algorithm. So models. So these are your three models, W1, W2, and W3. Now it is saying select the most appropriate match for these vectors. Okay. So uh, see let's first see the options. So these are your options. So you have to basically match, you know, the algorithm with the model. So W1 can be matched with linear regression or the regularized versions. Okay, so you have to check which of them matches with which one. Okay, so just have a look at the models. So you can see W1 is this. Now carefully see the weight vector. Okay, see the coefficients for the corresponding parameters. So 0, there is one 0, there is one 0.25, then there are two more zeros. Okay, for so x2, x2, x4 and x5 have the corresponding coefficients as 0. So basically this is a weight vector which is a sparse vector. Okay, so sparse vector is a vector in which most of the coefficients are 0. So W is a sparse weight vector. Now tell me which regression produced sparse vectors.
Lasso, sir.
Yeah, lasso, right? So lasso pushed most of the coefficients to 0. Then okay, so W1 sure will be lasso. And then what about W2? See, most of the coefficients in W2 are non-zero, and you can see, okay, so they are non-zero. That is for sure. Okay, for now that is fine. Now see weight 3, 0.24, 0.003, 0.1, 0.002, 0.009, and 0.14. So if you see the coefficients, if you compare the coefficient between these two vectors, this vector has all the coefficients pushed close to 0. So which regularized version or unregularized version created these types of models?
Ridge.
Ridge, right? So W3 is a ridge, ridge regression weight vector, and W1 is a lasso. So last W2 left is linear regression. Okay. So I'll just write the answer. So I've written it here. Okay. Any doubt here?
Sir,
Excuse me,
how
sir.
W3 is sir?
Yeah.
Sir, how is this? You are doing the W1 is lasso, W2. Is that given in the question?
Oh no, we have to find this, right? W1 is lasso.
These
Okay, so
observations like you have made from the question, or like these are the. Okay, sir.
these are
The
the
option.
observations which will
Okay.
give us the answer, right? So you have
Okay,
to
sir.
watch the vectors carefully.
Sorry, I did not see the question, sir. Okay.
Okay, okay, fine. Uh,
Sir, how you concluded that it's ridge for W3?
so see, W3 is not a sparse vector. That is, most of the coefficients are not 0. So you have to compare between W2 and W3. If you see, W3 has most of the coefficients pushed close to 0. Okay, so they are pushed close to 0. So that
Yes, sir.
was
It
the
will be ridge
ridge
regression.
regression.
Yes.
Okay,
Okay, got it, sir.
okay. Now this one. Uh, yeah. So consider a binary classification data set. Classes are 0 and 1 with two binary features. So I have drawn this diagram. See this closely. Okay, so there are two binary features, F1 and F2. Okay, two binary features. Keep this in mind. Okay, so f1, that is f1 is either present or not present, so binary features. Okay, a naive Bayes classifier is learned and the estimated parameters are given as this. So basically pf1, that is first parameter is present. Okay, first feature is present given that the data point is classified as 0, is 2, so this is the probability, and so on. So if you remember, this is nothing but p of, so what is this? P of 0, what should be here? 1. This is p hat of 0, okay, 0 from here. Then this is p hat of 2, and so on, right? So this is p hat of 1, subscript is 1, and so on. So 1 and 2. Okay, so all these values are given. Now now they are saying if a data point 1 0, so this is your x test, is predicted in class 0 by this classifier. So this x test is predicted as 0. What will be the possible values for estimate of py is equals to 1? So now they are asking what is p hat. So do you remember the generative story? So it was this, right? Then you had all these features which had the corresponding parameters. So there are two parameters, f1, f2. Similarly here, f1, f2. Okay, so this was given that it is labeled as 0. So p hat of 0, 1, first feature is present. Then p hat of 0, 2, second feature is present. Then rest of the two parameters also. So 1, 1, p hat of 1, 2. Okay, so how many parameters are there? 1, 2, 3, 4, 5. Okay. Now it is saying assume that the tie breaking goes to class 0. Values in the option are correct to do decimal places. Okay, so they are, oh sorry, I forgot this. What will be the possible values for estimate p? So basically they are asking us to find p hat. Okay. Yeah, so I have written down all these values which are given in the question. Now, how what is the decision function in naive Bayes classifier? You have to calculate this probability and you have to calculate this probability, and whichever is greater, the point will be labeled as that one, right? So we have to calculate py of 0, that is given the data point, what is the probability of the point being labeled as 0, and you have to calculate the probability of given the point, what is the probability of the point being labeled as 1. You have to check which one of them is greater. So now they have said in the question that it is predicted as 0. So obviously this one is going to be greater, right? That's why it was predicted as 0. So I have written, so I okay, now I have to write this probability. So what is your point? 1 0. If you check, it is 1 0, right? 1 0. So this is your x test. So now you have to calculate this probability. So you know what is this, right? So py of 0 will be 1 minus p hat, which we are trying to calculate this part. Then so this is basically p of y, p of x given y, right? This part is p of x given y. This is p of y. Similarly, this is p of y. Okay, so this is p of y is equals to 1, and this p of y is equals to 0, and this is p of x given y is equals to 0. This part and this part. So you have to calculate that. So I have written what is p of y is equals to 0? It is 1 minus of p hat, right? Because this is following Bernoulli distribution to determine the labels. Okay, so p hat, so that's why this is 1 minus p hat, because y is equals to 0. Then you have to write p1, since first feature is present, so you would have to write p, given that it is labeled as 0, first feature is present, so I've written this 0.2. Then second feature is absent, so that would be 1 minus probability of the point being labeled as, sorry, feature being present, given that it is a what, it is a labeled as 0. Okay, so 0.5, check this. Okay, so 0.2 and 0.5. So 1 minus 0.5 will give you 0.5. Then you have to write this probability. So just write it. So p of y is equals to 1 is p hat, you know that. Okay, then first feature is present. Okay, so p hat 1 subscript 1. Then second feature is absent, so 1 minus p hat 1 subscript 2. Okay, so 0.6, 0.6. So see, p1 hat 1 1 is 0.6, and 1 minus p hat of 1 2 is 0.4, so that's why 0.6. So 1 minus 0.4 is 0.6. Okay, so now you have to just solve this inequality. So this will be 0.1, you can see that. So at the end you will get this. P hat should be less than 0.217. Is it clear?
Yes, sir, clear. But I just want to ask one thing, that
Yeah.
label 1 is considered as a success.
Label 1 is considered at, yeah,
That's why you take p hat, and here
yeah,
where the level is 0, you considered 1 minus p hat.
yeah.
Okay, sir. Thank you.
Okay. Okay, so you can check the answer. It is coming out to be correct, 0.22. Okay, so they have asked you the range. So since it is a probability, it will be 217. Okay, so less than equal to, so this is closed. Okay, so next, okay. Okay, so this question is very trivial. So it is saying if pi of y is equals to 0 for y is equals to 0. So basically they have given you pi of 0. Okay, superscript 0, subscript 1. So they have subscript I. So they have given this. Now they are saying if this is true, then this is true, where y is equals to 1. So basically if so what they are saying, if pi of 0 is equals to 0, this implies pi of 1 is equals to 1. So what they are trying to imply is, that is, if pi is of 0 is 1, then 1 minus pi of 0 is equals to pi of 1. So that is not true, right? So this is false, because they are not at all related. You can see it here. So are these two related at all?
No, sir.
No, right? There is, yeah. So that is false. Okay. So false. Okay. Now a linear regression model is trained on a data set. It achieves zero training error for any label vector y. Okay, any label vector y. So this part is important. It achieves zero training error for any label vector y. Which of the following options will necessarily hold true? Here I denotes an identity matrix of appropriate size. Okay, so I have not written the options. Yep. So it should. Uh, okay. So yeah. So which of the following option will necessarily hold true? Here I denotes an identity matrix of appropriate size. So it has said that there is zero training error for any label vector y. Okay, that is, so this is your label vector, and this will give you your prediction vector, right? X transpose W will give you a prediction vector. Okay, is it clear? Is it clear? Is this part clear till here? Hello.
Yes, sir. Clear, clear.
Okay. Okay. So Yeah. So y hat is x transpose w. Now they are saying for all y hat is equals to y. Okay. So now see what does this mean? So do you remember this ax is equals to be a system of linear equations? Do you remember
Yes.
Yes,
this?
sir.
So tell me, when does this solution have a system? Tell me in terms of a subspace of column vectors of A and B vector. Tell me in these terms. A solution, a system of equations will always have a solution when the B vector on the RHS lies in the column space of this matrix A. Okay, then it will always have a solution. Are you getting this? So it is saying, so see, x transpose W is equals to y. Now you compare this to this equation. So basically, the column, so x transpose W columns subspace contains vector y. Okay, and it is saying for any y. So see, x transpose is a n cross d matrix. Okay, so columns of this data matrix will belong to Rn, and y also belongs to Rn. Now it is saying for all label vectors, all possible label vectors, this holds true. This means that x transpose is a full rank matrix. What will be the rank of this matrix? N. Okay, it will be n. Now when x transpose is a full rank matrix, x transpose is always invertible. Are you getting this?
Yes.
So for any y belongs to Rn, x transpose W is equals to y. This implies x transpose must be full rank matrix. Okay, that is the subspace spanned by the columns of x transpose is equal to the Rn itself. Okay, I hope you are clear with the subspace part, right? So x transpose is invertible. Okay, so I've written this y hat is equals to x transpose W star is equals to y. Now W star, you know the closed form solution for this, which is x transpose pseudo inverse xy. Now since x transpose is already invertible, this becomes inverse. Okay, so W star is this. Now y hat was this. Okay, so y hat is x transpose W star. Now I just substitute W star here. So I've got this. Okay, so this is your W part, W star. Okay, and y hat is equals to y. So I've written that. Now y is equals to some matrix into y. So should this be identity matrix? So this part is actually identity matrix. Is it clear? So you can match the answer. So this part needs to be true. Okay. Is this part clear? So see, if you are clear with this part, the full rank part, then it's fine. Is it clear? Anyone? Any doubt? No?
No, sir. Sir, but any other approach to do this question?
No. This is the only approach. So basically, this statement was there to, you know, make you jump to this conclusion. Okay.
Okay.
Uh, yeah. So now, let W be the solution of linear regression model, and W tilde be the projection of W on the linear subspace spanned by the data point. Now, during the explanation of kernel regression in the lectures, you got to know that the W which we find in linear regression lies in the span or
Features.
subspace of data points. So if you remember, W was nothing but X alpha. Yes or no? So now when W itself, which is the solution of linear regression model, lies in the subspace spanned by the data points, then W's projection on the subspace spanned by the columns of this data matrix will be W itself. Okay. Yes or no?
Yes, sir.
Okay. Suppose there is a vector. Okay. Vector, and it lies in a subspace. Then I ask you, what is this? So do you remember this? Projection of W, this property, projection of a vector onto a subspace is equal to the vector itself if W lies within the subspace. Okay. So now the options become very easy. Training error for W, since W and W tilde are same, so training error for both will be same. Okay, so this option is very trivial. Then W is equals to W tilde. Okay, so I've now next, training error for W is not equals to W tilde. That is wrong. Okay, so I've written the explanation. Okay, again, you might feel like I am, jumping randomly from statements to statements, but these are very easy questions and they have been, direct observations in the lectures. So there is not much to explain. If you remember where they are coming from, you will immediately, uh, find the answer. So W, the solution of linear regression, lies in the span of the data points. This implies, okay, so this statement implies W is also W tilde itself. That is, so this was projection of W. Okay, so if a vector lies in a subspace, the projection of the vector onto that subspace will be the vector itself. Okay, so this is the uh, statement used. So training error for W is also training error for W tilde. So those two above options are correct. The last one is wrong. Okay, maximum a priori probability estimate for linear regression weight W is equivalent to ridge regression. Which of the following conditions make the above statement true? So yeah, okay. So in ridge regression, we did Bayesian modeling, and the prior we had on W was this, right? Falling normal where mean is 0 and the covariance matrix is I, and this. Okay. So multivariate normal distribution was assumed as a prior for the W. Okay. So this option is correct. Is this
Yes, sir.
clear? Then Y given Xi was okay. W transpose X sigma square. Again, nothing much to explain, right? Yeah. So yeah. So prior on W was this, and the distribution of distribution of probability for this variable was taken as this again. And in the lectures, sigma square was taken to be 1. That is the variance. Okay. So not much to explain in that either. Okay. Now this, I think, yeah, we have to solve this one. Okay. So this is a good question. So I won't show you the solution first. So suppose you, okay, please pay attention and tell me the answer. Okay. First you have to solve this, then I will solve it. Suppose you want to use the naive Bayes classifier, good, okay, to predict the gender of a person based on two features. So this is hinting you towards the naive Bayes classifier, which you learned in week 8. Okay, so there are two features, height and age. So one feature is height and the second feature is whether their age is above 20 or not, above 20 or not. So I'll give you a hint. F2 is a binary feature. Okay. So is F1 a binary feature? Height?
No, sir, Gaussian.
Yeah. So assume that the features f1 and f2 are conditionally independent. So class conditional independence is given. This means generative story 2, right? Given the gender of the person, and that the variance of the height distributions are equal. Okay. So variance is this should also hint you that height is following a normal distribution. Okay. So variances of the height distribution are equal. How many parameters are required to classify new example using naive Bayes classifier? So anyone, just I'll give you 2 minutes, think and then answer. Okay. In the meanwhile, I'll just mute the. Okay. So think and then answer.
There are 6 parameters.
Others, please continue doing. I'll ask after 2 minutes. Okay. So uh, his answer could be correct or could be wrong also, unless you already know. Okay. So anyone else who has come up with the answer? Anyone? Okay. So just okay. No one? Anyone? Okay. Please try to solve it. At least think about it. Anyone who might not have done the rough work but still came up with an answer?
Sir, maybe 5, I think.
Okay, five. Five is one possible answer. Then six is one possible answer. And anyone else?
So
Four,
here
five.
variance is same or mean is same.
Variance is same for. Okay.
Variance is same. One
So
from
someone
here.
said four also.
Okay,
How about
so
three? How about three? Can we directly use 2D plus one?
5. So six. Six would be answer.
Can we use 2D plus one formula which we studied? So according to that, the answer would be five. So can we use that? So if someone jumps blindly to this, he will end up
No, so
committing a.
actually, I used
Yeah.
in a
Okay.
session. Vishal sir said to me, and he was explaining the question like he was taking
Okay. Okay. Okay.
one
Fine. Fine.
parameter from there.
Fine. I'll explain. Okay. So
Sir, 2D
yeah,
plus 1 is applicable for binary features only, not for Gaussians.
yeah, binary features. Okay. So that will be wrong. Okay. So see, f1 is a height, so it is following a normal distribution. So mu1 comma sigma square. F2 is a binary feature, so there will be one this, so p male, and this is present. Then there will be p female, and this is present. Okay. So this is one feature. This is one, and they are saying that variances are same for the height distributions. Okay, pf1. So basically these two, F1 and this F1 and this one are following same variance. So mu2 comma sigma square. So how many parameters are there? So first one is this one, 1. Then second is this one, mu1. Third is this mu2. Then since variances are same, this is the fourth one. Don't count it twice, fourth one. Then you have fifth one this and sixth one this. So there are total of 6. Okay, so 6 is the correct answer.
Yes, sir. We answered 6.
Okay. Okay. So I've written this answer. So generative story 2 is chosen. So assumption of class conditional independence. Then F is a binary feature. This is a real feature, real valued feature. So Gaussian. Okay, so Gaussian. So I've written, so first is this, first, second, third, then common, fourth one, then fifth, and then sixth. Okay, so mu1, mu2, sigma square, p. So this is 1, and okay, so p superscript 1, subscript 1, p superscript 0, subscript 1. Okay, so there are 6. Okay. Now this one, consider a naive Bayes model trained on the following data set. Okay, so this is your data set where X is a D cross N matrix and this is your label vector. Assume that P hat, okay, and P hat superscript yi, which is your label, and J are estimates for Py is equals to 1. Okay, so again, always draw the generative story. Okay. So they are that. Here, features, okay, that is all jargon. These parameters are estimated using MLE. If a test point label has label 0, what will be the probability that the point is 0 0? So first of all,
1.
tell me. Yeah, okay. First of all, tell me what are we trying to find? Yeah, just tell me. P like x given y given x, x y. What are we trying to find?
Sir, y
Probability of
equals
0
to
0.
0. Y equals to 0 if given x text is equal to 0 or 0.
Okay, one answer is this. Anyone else? So see,
Probability of
go on.
probability of x equal to 0 0 given y is equal to 1 into probability of y
Yeah,
is equal to 1.
correct. Okay, so we are trying to find this, not the other way around. Okay, so we are trying to find this. So read carefully. If the test point has label 0, so given the label is 0, what is the probability of this? Okay, observing this point. Okay, so we are trying to find this. So first of all, what you should do is find the parameter estimates. Okay, so data set is given to you and the label vector is given to you. So you have to find the parameter estimates. So what is p hat? P hat is the fraction of males, not males, fraction of data points labeled as 1. So you have to count how many data points are there? 3. Out of those, how many are labeled as 1? 1. So 1 by 3 is the parameter estimate for p hat. Then we have to calculate this, 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 and this. Okay, so what is p hat superscript 1 subscript 1? It is fraction of males, fraction of data points in which first feature is present, given that it is labeled as 1. So first of all, see how many are labeled as 1? Only 1. And in how many first feature is present? Only 1. So 1 by 1, that is 1. Then you have to see p hat superscript 1 subscript 2, that is the fractions of data points in which second feature is present, given that it is labeled as 1. So you have to check among the label points which I have labeled 1. So there is only 1, and in this one data point has feature f2 present. So again 1 by 1. So 1 by 1. Now you have to similarly calculate this and this. Can you calculate this? So p hat superscript 0 subscript 1, that is fraction of data points in which feature 1 is present, given that it is labeled as 0. So you have to check all the data points which are labeled as 0. So there are 2 data points, and out of which in only one feature 1 is present. So 1 by 2 is the answer. Okay. You can see here feature 1 is absent. Now you have to calculate p hat superscript 0 subscript 2, that is fraction of data points which are labeled as 0 in which second feature is present. So you can see in both of the data points labeled as 0, feature 2 is absent. So 0 by 2. Clear? Now you have to calculate this probability. So what will be this probability? See, when you are calculating p of y given x, what do you do? P of y into p of x given y. So you just have to calculate this one and not this entire thing. Okay, so you have to just calculate this part, and you know how to calculate this part, right? So basically this would be just, so see, the data point is 0 0. So yeah, first feature is absent, right? First feature is absent. Okay, okay, first feature is absent. Okay. Okay, so this would be 1 minus. I did a mistake here. 1 minus. Okay. So first feature is absent, second feature is absent, given that it is labeled as 0. So what was P1? P1 was, okay, P1 of 0 was, yeah, so it was 1 by 2, so no change happens, right? So you'll get the same answer, which is, so P2 is 0, if you can see, P2 superscript 0 is 0 from here. Okay, so 1 minus 0 will give you 1. So this will give you 0.5. Is it clear? Anyone any doubt? Anyone any doubt how this all unfolded? This question? Anyone?
Sir, no any
Okay.
doubt, but I want to make one thing clear.
Yeah.
Actually, I want to see question. In a question, uh,
Yeah.
not this one, sir. Yeah, sir. From here we can easily see that data already 0 0 is coming from label 0. So why
Huh?
it would be probability would be 1
Sorry.
because it's the same from test data, training data. I mean training data.
Okay.
0 0
So
is
from
present in
training
training
data,
data.
you are learning a model, and then you are using that model to predict. Okay. Are you getting this? So all the other points will also have an influence on the data, right? So they will give you some model, then you will use that model to again check it. What happens in an ML algorithm? You use the training set. Okay, so tell me.
Yes, sir.
Uh, okay, so when you have a training set, okay, you get a model from it. Okay, you get a model from it. Then
When we apply on the test data.
you get a model from it. Then you again apply it on the training data also. You'll get some error. That error is not always 0. Okay, that error should be minimum. Then if error is good, like very less, then you will use it to check the test points also. Okay. Okay, so if you have got a model, it does not mean that it will always, predict correctly on the trained data also. Are you
Okay,
getting
sir.
this?
Yes, sir. But in some question, what I saw
Because see,
that
see, at the end you get this model, right? It is still doing a mistake on this point.
yes, sir.
Okay, on the training set it is still performing mistakes. Okay, then fine. Okay, if you still have doubt, you can ask at the end, right? I have to cover one more paper. Okay, so Gaussian kernel regression with parameter sigma square is equals to 1 by 2 was applied to the following data set. Okay, so kernel regression. Okay, so linear regression. Okay, so this is your data set and this is your label vector. The weight vector can be written as W is equals to phi x, which is your transformation, which we don't know, right? And alpha vector. Okay, where phi is the transformation mapping corresponding to the kernel. Vector alpha is given by this vector, which is obtained as k inverse y, where k is a kernel matrix. What will be the prediction of point this point? So first of all, tell me what is the formula for kernel prediction? Label prediction in kernel regression. Y prediction. Okay, first of all, one more thing. Tell me, can you throw away the dataset after applying kernel regression?
Sir. No, sir.
Okay, so you
We
cannot
all,
throw it
yes, sir,
because
we
it is a,
always need a training data set.
yeah. What about regression, normal regression?
So, no, sir, we can throw in normal regression because we have a model.
Yeah, okay, correct. Okay, so yeah, so if you remember, Y prediction formula in kernel regression was this. What was it?
Sir, alpha into kernel of xi of x test.
Okay, so you can see that your xi's, which are your data points from the training data set, are still being used in the prediction. So you cannot throw away the data set. Okay. So this is your formula which we will be using in this question. So alpha they have given you. Alpha. So these are your alpha i's. Okay. There are 4 data points. First data point, second data point, third data point, and fourth data point. So you just have to use this formula. Y prediction is equals to summation of alpha I star kernel. So you have to use this kernel function, and they have told you which kernel function you have to use. Gaussian kernel function. What is Gaussian
Gaussian
kernel
kernel.
function?
Sir, it would be exponential of norm of xi minus xj of square and upon 2 pi square.
Xi minus
Xj upon 2 pi square.
2 sigma square.
Yes,
Okay.
sigma square, sir.
Yeah. So this is the formula you will be using. Okay. So in this Gaussian kernel regression, now just use this formula. So alpha i's are this. So alpha 1 is 2.1. So I've written 2.1. E raised to the power of negative norm of, so what is xi x1 is 10. What is your, okay, what is your data point x test is 11. Okay, so I'll just remove this all this all. Okay, okay, so just place the values 2.1 minus 2.130, and you have to calculate this e raised to the power of negative of norm squared of subtraction of these two vectors 10, which is your xi minus your test point, which was your 1 1 1. Okay, okay, so if you do this, this will give you 0 1 vector, right? 0 1 vector, 0 negative 1 vector, whose norm will be 1. So okay, 2.1 e to the power of minus 1, then minus 2.1 e to the power of minus 1 again. If you do this and calculate its norm squared, that would be 1. Okay, and negative 1. So these two will cancel, these two terms. Then you are left with this plus 3e raised to the power 1 minus 1. So this will be 0. So e raised to the power minus 0 will be 1. And you have 3. And then last one is 0. Last coefficient. So you need not calculate this even. So you will get 3. Is it clear? Okay, so 3 is the answer. Anyone? Any doubt? See, if you have any doubt, you can ask. Right. Okay. Okay. Now, okay, this is a good question. Okay, so I'll give you 3 minutes. So okay, so this is a good question paper. Okay, so because the questions are little bit tricky. So if you are not paying attention to the question, unlike other question papers, you will most probably do a mistake. Okay, so I'll give you 3 minutes, solve this, and after 3 minutes only tell me the answer. Okay, don't try to tell beforehand. Okay, let others do, and then I'll just open the question here and just tell me the answer. Okay, think about it carefully. So after 3 minutes, okay, just see the I mean time here. So it's right now it's 1 minute past 9. So I'll ask you at 4 minutes past 9. Okay.
Sir, just so question. Yes, sir. Sir, can we answer?
Okay. So yeah. Anyone?
Sir, 400 data points.
Okay, 400 is one answer. Then anyone else? 600 is one answer. Okay. Then anyone 900? 900? Anyone? How about 1000? Okay. So 600 and 400. So okay. So just follow on with me. Okay, follow along. So suppose we have a binary classification data set with 1000 points consisting of 600 points belonging to class 0 and 400 points belonging to class 1. Okay, now if we use k nearest neighbors with k is equals to 900, so parameter is set to be 900 to predict the class label of the data points. How many data points will be classified correctly? Okay, so see, first of all, try to try to go through the algorithm. So first of all, you have a point x test. not X test, sorry. Okay, so first of all, see what you have to do is you have to calculate 1000 distances. So for any X test, you have to calculate 1000 distances. Yes or no? Tell me. You have
Yes,
to
sir. Yes,
calculate,
sir.
okay, 1000 distances. Now it is saying k is equals to 900. So out of those 1000 distances, you have to pick the 900 minimum distances. Okay, so whichever 900 points are closest to X test, those will be picked. Okay, then you have to calculate the majority of the labels among those points. Okay, so whatever is the majority will be given as the label for X test. Now see, you have 900 points. Okay, possible points which are chosen as the closest ones. Now you know that 600 points belong to class 0 and 400 points belong to class 1. So now suppose out of those all 400 points which are labeled 1 are selected, okay, are closest. Then how many will be left? 500.
Yes, sir.
1 and 500 with, so these 500 all will be label 0 or not? Yes or no?
Yes,
Yes
sir.
or no?
Yes, sir.
So is the majority label 0? Is the majority label 0?
Yes,
Yes,
sir.
sir.
Okay, so majority label is 0. Now you know that majority label is 0. So out of these 1000 data points, how many points are labeled 0? 600. So 600 will be correctly classified and 400 will be wrongly classified. Yes or no? Tell me. Anyone having any doubts here? So see, I've written this in simple English. Okay. So see, 1000 data points, 600 points belong to class 0, 400 belong to class 1. Now k nearest neighbor is applied. K is equals to 900, which is a hyperparameter. Okay, if k is 900, at least 500 points will have label 0, given all the points 400 points with label 1 are included in the closest 900 points. Okay, so at least 500 points with label 0 are there, so majority will be label 0. Okay, so all test points will be labeled 0. Okay, always. So now you have to see, so there are 400 points with label 1, all those are labeled as 0. There are 600 points with label 0, all those are labeled as 0. So there are 600 points which will be correctly classified after applying the model. Is it clear? Anyone had any doubt?
Yes, sir. Why 500 will be picked, sir?
No. See, I see. There are 900 points to be picked. Okay, there are 900 points to be picked. If you, if if all the 400 points with label 1 are included, okay, just pick them up. So there cannot be 450, right? Because at max there are 400 points with label 1. Yes or no? Yes or no?
There can also be 600 plus 300.
Yeah, so 600 plus 300. Again, see, we are taking the worst case scenario. So 600 with label 0 and 300 with label 1, right? So I'm taking the worst case where there are 400 points with label 1. I'm maximizing the chance of ever achieving a label 1. So there it is 1. 400 points with label 1. Then also you will have 500 points with label 0. So now no matter how much you increase, so you can go only up to a certain limit. So at that maximum case also, you will still be labeled as 0. Are you getting this? Because majority will be 500 points. Are you getting this? Are you getting this or not?
Sir.
Sir, what is meaning of it is earlier leveled 400 and again it is getting leveled as something. Earlier it is given that
So
400s are
that
level.
is the test set. When you are applying the k nearest neighbors model on the test set, Then those 400 points which were labeled 1, so this is your y actual, and this will be y predicted. So y predicted will be 0 for all those 400 points which are actually labeled as 1. Okay, so 400 points will be wrongly classified, and 600 points which were already labeled 0 will anyway be labeled 0. So this model will always label any point to be 0. Are you getting this or not?
Yes, sir. Yes, sir. Clear.
Okay. Yeah. So now we have a question on cross validation. Okay, so suppose we have 1000 training examples and want to compute 10-fold cross validation error. This error is calculated as average of errors obtained from n1 iterations of cross validation process. So first of all, what happens in cross validation? There are different hyperparameter choices. Okay, not, I should not take lambda 1. Okay, so yeah, lambda 1 is a correct hyperparameter in linear regression case. It's ridge regression. So suppose this is one hyperparameter HP1, then HP2, then HP3, then HP4. So what you do is in 10-fold cross validation, you will pick one hyperparameter value. Then you will divide the data set into 10 equal parts. Okay. Okay, so I have drawn this diagram. So okay, so they are asking what is the value of n1, n2, and n3. Okay, so just read the question. The error is calculated as average of errors obtained from n1 iterations of the cross validation process. Each iteration involves training a model. Okay, training a model with that hyperparameter picked value. Okay, on a subset of size n2 of the training data and evaluating its performance on a disjoint subset of size n3. So basically, you have to tell all the values. Okay, so see, what the user will do is, suppose I pick 3 values of a hyperparameter. Suppose you are using k nearest neighbors. So you have to pick a value of k, right? So what I will do, I will pick 2, I'll pick 3, I'll pick 4, I'll pick 5. So I have to now check. So what will happen is I will use this as k value. I'll get a model. I'll evaluate the performance of that on this set. I'll get some estimate. Then I'll use this as the k value, get a model, train it on this, test it on this. I'll get some value, some estimate, then this, and then this. And then whichever is giving the minimum estimate, I'll just pick that value. Are you getting this? Now the actual what happens in a cross validation. Are you getting this? So see, I'll explain. So see, first of all, how many data points do you have? 1000 data points. Okay. So how many fold validation you have to do? 10-fold. So what happens in 10-fold validation is you will divide the 1000 data points into 10 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you have divided into 10 bins of 100 points each. Now what you are doing, you are picking this, you are keeping this F1 aside. You are training the model on the rest of the folds, 9 folds. Okay, you will get a model. Okay, you will get a model from these 9 folds. Then you will use that model to test. You will use that model and use this set, the left out fold, for checking the performance of it. Then you will get some error. Okay, so you will keep it aside, E1. Okay, then what you will do is you will keep this set as a validation set and train on the rest of the folds. You will get a model, you will check its performance on this left out set, you will get E2, and so on. You will use each of the fold as a validation set, so you will get 10 errors. Then you will average them out, you will get some error. Okay, then you will pick this value. Same process goes on, this value, same process go on, this value, same process go on. So whichever has the least average error will be picked as the hyperparameter. Is it clear now? So see, so for lambda 1, so first I'm keeping this fold as validation set, then this fold, and so on. At last this last fold as the validation set. calculate E1 error, E2 error, E10 error, then average them out. You will get average error for this parameter. Similarly, now you will pick lambda 2. Okay. Then you will do the same process. You will get some error. And then whichever has the least average error, you will pick that lambda. Is it clear? This should be very clear now. Yes or no?
Sir, what is lambda 2?
So lambda 2, see here, there was another candidate for k, right? So this is lambda 2. So this is one hyperparameter value. Then this is another hyperparameter value. Okay. So what is the appropriate value of n1? So how many iterations are there for a particular lambda? 10 iterations, right? Corresponding to each validation fold. So there are 10. So n1 is 10. Then model of subset n2. So see, after leaving the validation set, how many data points are you left with in an iteration? Tell me. So there are 1000 data points in
9.
this fold. I have 100. How many are left?
900.
Okay, so 900. Then what is the value of n3? So n3 is a disjoint subset on which you are testing, evaluating its performance on a disjoint subset of size n3. So what is n3? n3 will be 100, right? Because you are testing on single fold and each fold has 100 data points. So n3 would be 100. Is this part clear? Is this part clear?
Yes, okay.
Yes, sir.
Okay. Now,
Sir, for the previous question, how many data points will be classified correctly? The answer was 400.
no, it was 600, right? Okay, 600. So classified correctly means the predicted label and the actual label match. So here they are matching. So there are 600 such points.
Okay.
Okay, now this question. Okay, so first of all, you should know entropy of a node. What is entropy? P log minus of P log P plus 1 minus P log of P, where P is the fraction of points labeled as 1, or you can take it as 0 also. Okay, it's up to you. Okay, fine. So consider the following training dataset for binary classification problem on the left and some decision tree for the right on the right. The labels lie in the set +1, -1. So all these pluses are +1s and negatives are -1, as you can see. Okay, both features are positive. Okay, both features are positive. That is, you only have the basically the first quadrant of R2 plane. Okay, now L1, L2, L3 and L4 are leaves. So these are your deciding nodes, right? Leave nodes are one which decide the label. So these are your leave nodes. The four dotted lines are drawn for your reference. Okay, they might or might not be. They might be or might not be a decision boundary. So that is not correct. I mean, sure. So both features x1 and x2 are positive. Our focus will be only on the first quadrant. Use log2 for all entropy calculations. Calculate all the intermediate quantities up to 3 decimal places. Okay. So now first question is this. What is the label of leaf L2? So check. So
Sir,
first of all,
sir, in the last, like, so the formula that you have written, 1 minus P log 1 minus P should come, right? At the last term.
yes,
Last
yeah,
term.
so yeah, it's 1 minus P. Okay. Okay.
Okay.
Okay. Okay. So, okay. So try to do this. I'll just wait for 1 minute and then I'll ask. Okay. Sorry, 2 minutes. I'll ask. Let's start.
Yes,
Sir,
sir.
it should be 1.
Yes, sir. L2 would be positive, L1 negative, L3 negative, and L4 also negative.
Okay, let's see. Okay, so first question which is being asked on feature 1 is my x1 less than a? Okay, so x1 less than a.
We will come in this region. Yes, sir.
Okay, so this region. Then x2 less than c. So second feature. So you have to check up along the y-axis. So x2 is less than c. So this point. So if it is less than c, then you end up in this leaf L1. Okay. So this. Now, yeah. So if it is less than c, so you can see all of the points are negative. So this is a L1 will be
Negative, sir.
yep, negative. Okay. And all those who are greater than c, they will be labeled as
Positive. So that's why L2 is positive.
okay. So L2 is positive. Okay, so L2 is positive. Then okay, now the right part. Okay, so for all those points greater than okay a with feature 1. So now x1 less than b, x1 less than b. If they are less than b, then all these points will be labeled as negative. Yes or no? X1 less than b, they will be labeled as negative because majority of
Yes,
them.
sir.
Okay. Okay. Then yeah, all these will be positive, right? They are greater than b. So now I'll draw the decision boundaries, actual ones. Okay. Okay. So any point in this L-shaped region, inverted L, okay, will be classified as negative, and any point in these green regions will be classified as positive. Clear? Yes or no?
Yes, sir.
So this part is your L1. Okay. This part is your L2. The this whole part is your L3. This whole part is your L4. Okay. Uh, Fine. So okay. So L2 is L2 is positive, as you can see. L1 is negative. So L1 is negative here. Okay. L4 is positive. L4 is positive. Then L3 is negative. So only these L4 and L2 are asked. So you can just answer them. Okay. Now, so these are multiple part questions. Okay. Select all the two statements regarding the decision boundary of the decision tree. The dotted line x2 is equals to d is not a part of the decision boundary. That is not a single point on x2 is equals to d is a part of decision boundary. So x is equals to d. So is there anywhere there is a boundary along d, dotted line d? No, there is not even a single line, right? Horizontal line along the d dotted line. Yes or no? So is not a part of the decision boundary. Okay. So what are your decision boundary in this? So one is this L shaped line. Okay, this line. This is part and this is part. Clear? This red line and this green line. Yes or no? Okay. So just keep that in mind. So the entirety of the dotted line x1 is equals to a is equals to is a part of decision boundary. That is, every single point on the dotted line is a part of decision boundary. Okay, so tell me, is it true? Yes or no?
Yes, sir, it's true. L1 and L2 both are getting separated.
Then this third point, entirety of the dotted line x2 is equals to c is a part of decision boundary. That is, every single point on the dotted line is a part of decision boundary. So x2 is equals to c. Okay, so is it? So is this part anywhere covered? This part?
Only one third.
Not right.
So in the second option, when we say x1 is equal to a, which line exactly are we referring to?
This one.
So sir, in this one, earlier when we were making the decision boundary x1 is less than a, it was covering the whole a line. But now it
Yeah.
is not
No,
covering
no.
the
So,
whole
so
a
see,
line.
in the very first question itself, this part is also playing a role, right? So if it is to the left of this, it is playing a part in the decision function.
But the final boundary that we made, the some of the a part is not included now. So option will not be correct, I believe.
Yeah, that is okay. Okay, just wait one minute. The entirety of the dotted line. Okay, okay. So yeah, I forgot this one. So yeah, according to this word, this should not be correct, right? Entirety of the dotted line x1 x2 is not a part of decision boundary. Okay, just wait one minute. Let me see the reference.
Sir, we are separating two leaves, right? So L1 and L3, so it should be right.
L1 and L3. L1.
But the AC has no role in separating the L1 and N3, right?
Okay, just wait one minute. Then x2 is less than c. Okay, x1 is less than a. This line. then x2 is less than c. Yes. Okay, then x2 is less than c. So this is okay, L1. Then this is L2, this part, which will be green. Okay. This one is less than B. Is less than B. Then okay, this is all. Okay, just wait for 1 more minute. I'll check in my book. Okay. Okay, so hello. Yeah.
Yes, sir.
See, this should be a decision boundary because we are basing one of our question on this entire A part. Then okay, then according to that, this C should also be there. Okay, so I think this option should not be correct, right? This one,
Yes, sir.
because entirety of A is not being used at the end. So this part is not being used. Okay,
Bonus marks.
again I'll have to confirm with my instructor. Okay, so this option, just leave it for now. I'll check.
Sir, I didn't understand why it should not be the right answer.
Because in the diagram you can see that at the end this is one region. This region is separate.
They are all negatives, that's why, no?
Yeah.
But two leaves are being separated from that, so won't that be considered?
Two leaves are being separated.
Yes.
L1. and
We are considering boundary area
yeah,
area
that
is
is
separating the positive.
correct.
If we consider
But at the end, L1 and L3 are predicting the same thing, right?
Yes,
Sir,
sir.
Sir,
but
but
if we see through,
yes,
sir, but if
Branches are
we see
different.
through the x1 less than
Oh,
a, then
yeah.
it.
So definitely,
Sir,
okay,
they
okay,
are
yeah. So
different
basically,
sides.
we are dividing into different regions, right? L1, L2, L3, and L4. So you can see that here L3 and in this part, L3 and L1 are being separated through this.
Yes, sir.
Okay, yeah. So according to that,
but but sir, both are negative. So why are they separated?
No, x1 is less than a
because
and
see,
x1 is
this
greater
part,
than a.
this L1 part is this L1, this region label is being decided according to this leaf, while this one for
Okay,
this
sir, got
region,
it.
the
Yeah,
labels
yes,
are
sir.
being
Yeah,
decided according to this leaves. Okay, so yeah, according to that
one
you can
is one is less than A and one is greater than
both are from a different branch.
okay,
That's
just
right.
wait for 1 minute. I think there is some background noise. So yeah, so correct. Okay, so L1 and L3 are being distinguished by this part of the boundary. So a line is being completely used as a decision boundary, while C line is not being completely used. So this part is left. Okay, okay. So this part is correct then. Okay, but again I'll check with my instructor. Okay, so this part is obviously wrong because entirety of C line is not being used. Only a finite segment of the dotted line x1 is equals to b is a part of decision boundary. So B line is here. So you can see entire B line is being used. Okay, so that option is wrong. Is it clear?
Yes, sir.
Yes, sir.
Okay, now this one you can. Okay, I think we forgot about some questions. Okay. Okay, so see, there are some other questions also in this, which are uh, the entropy questions. So that you can calculate, right? Entropy of leaf L3, you can calculate easily, right? Okay, from the formula you can calculate. Okay, you first have to calculate the fraction, and then you have to take minus p of log 2 of p and minus 1 minus p log 1 minus p. Okay, so you can calculate that. I'm not doing that. Okay, direct formula is there. Okay, is it clear? Do you want me to do this?
clear, sir. We can proceed.
Okay, now information gain, again you can calculate, right? So they have given you the formula for the information gain of the entire tree. So entropy at root you will calculate, and then you will calculate weights for the entropy of leaves L1, L2, L3, and L4. Okay, and then you'll weight them and then subtract from the entropy of the root node. You will get the answers. Okay, now decision tree shows in the diagram is the best possible tree. That is, it achieves the greatest information gain from roots to leaves. So if you see, uh, okay, so it was actually this one, right? Okay, so if you see the diagram, this is not actually the greatest tree. There should have been a boundary here also. If you had asked another question, so what we did is we basically cut short the tree. That is, we didn't decide the hyperparameter correctly. We could have got a good tree which could have classified these as negative points, this part. Then we would have got a good tree, right? But instead we didn't do that. Is it clear?
Sir, even after they were classified, one more thing is that L1 and L3 are being separated. So that is one more thing which was not
L1 and L3 are being separated.
the one which we discussed earlier. So that was one more thing which is not good about this decision tree. They could have been in one region.
Uh, okay. How? But
Oh yeah, but they are separated by vertical lines. It's
yeah.
different. I don't
Okay.
think. Yeah,
No,
yeah.
no. Okay. So the only thing is these points are incorrectly classified. So we could have, grown the tree more, okay, in height, so that we could have
More
separated
depth.
these two also. Okay. So I've not written those questions. I should.
So the formula of information gain is different.
How is it different? Like information gain is? Tell me.
Sir,
And
entropy of parent minus
minus
there was some
summation of, first of all, gamma,
yes, sir,
Gamma.
gamma, gamma.
Gamma.
gamma, then
Entropy of
The entropy of left.
DL.
entropy of
D left.
leaves, and summation of all those gamma should be, oh sorry, not gammas. So basically you have to calculate for each of those leaves gamma and then calculate the entropy, sum them up and then subtract it from the root. Okay. Now this question, I think we are done with that. Okay. Okay. So you can do all those entropy questions by yourself. Okay, so that is false. Okay, so we have seen that there could be a even better tree. Now consider the following training dataset for binary classification. So the symbol plus is a data point with label +1 and negative is a data point with label -1. Okay. Based on the above data, answer the given question. How many points are misclassified by the classifier? So you can see on this part, the negative points are being misclassified, and on this part, the positive points are being misclassified. So 1, 2, 3. Okay, I should.
5 points.
Okay, 5 points. Okay. 1, 2, 3, 4, 5. 5 points. Okay. Now they are giving another question for this. How many? Okay. Consider another linear classifier with W, W dash is equals to 3 times of W. So basically they are scaling this W vector, but that wouldn't change our separating hyperplane, right? It
Remains
wouldn't
same.
change.
Yes, sir. Yes, sir.
Okay. So how many points are misclassified by this new classifier? Again, 5.
So same answer 5.
Okay. So I'll close with this. Okay, now a second question paper.
Hello, sir.
Yeah.
Information gain is equals to entropy of parent node minus gamma of entropy of left plus 1
Yeah.
minus
So
gamma of.
they, for that they have given you the formula, right? Usually the child nodes are used, but they have given you the formula for that, which is uh, entropy of root minus summation of weighted entropy of the leaf nodes.
Okay, leaf nodes.
They have given the formula if you see in the question.
They have
Okay.
given a simple formula that
Yeah, that,
entropy.
so that will be used, right? Okay, okay, we can do it at the end, but let me jump on the second question, I think. Second paper. Okay. Okay. So this is your 2023 September term paper. Okay. So consider a training data set where X belongs to, again, your X is your data matrix. Target Y belongs to Rn. Suppose a team decided to use a linear regression model Y is equals to W transpose X. So this tells you that we are searching in the space of linear models. This W transpose X tells you that, where W belongs to RD, obviously. Then what, which that minimizes the objective function LW, which is given below. So is this LW nothing but your squared error? So this is your Y predicted. These are your actual labels. Okay, so basically you're squaring the difference between the predicted and the actual label and then summing them across all the entire data points. Okay, so this is your uh, objective function. Now there is a W which minimizes this. So they have asked, let the dimension of D, so let D be 3 and N is 100, which is 100 data points. what is the sum of elements of x transpose w minus y. Okay, if you think the given information is insufficient, enter -1. Okay, so first of all, the w used here is 1, which minimizes this function. Now, do you remember the gradient of this function? Gradient of this function at this w star. So let's say that this is w star, because otherwise w is very general. So can you tell me for this w star, which we know minimizes this function, what will be the gradient at this value? What will be the gradient of the loss function?
Sir, we will differentiate it.
No, yeah. No. I am asking what is the value of the gradient. So tell me, when you find minima, okay, of a function, you know that at this point the minima of the function will be, sorry, gradient of the function will be 0, right? So I have the gradient function and I'm calculating its value as at this w star, which I know minimizes this objective function. They have given you this. So will this be 0?
Yes, sir.
And what is the gradient in this case? It was nothing but this only. So x transpose w minus w is equals to 0. From this you came to know x transpose w is equals to xy, right? And then you used to get the closed form solution, which is x transpose pseudo inverse of xy. Okay, so this is a very easy question. Okay, so now this is a 0 vector, this part, a 0 vector. So sum of all the elements in this will be 0 only. Yes or no? Are you getting this? Anyone, any doubt in this? So I've written this here. Okay, what is sum of the elements of this vector? So they have given that w star minimizes lw. So this means L of w star gradient of the function at w star will be 0. Okay, and we know the gradient is x transpose w minus xy. Okay, this implies. So w is equals to this. Okay, so we know that this is equal to the 0 vector. So sum of all those will be 0. The sum of elements of the vector. Okay, is it clear? Anyone, any doubt in this? Again, this is very weird, I mean, trivial question, but a little bit tricky to read it only, nothing much. Okay, so now definition of parametric.
Sir, can you go to the
Yeah,
previous ones?
okay. Yeah,
What actually we have to do here?
see, it is asking you. So suppose they have given you this. This is some vector. Okay, they are asking. So this is some vector of this form. They are asking you the summation of these elements in this, sum of these. Okay, now they have given you that this w here is actually w star, which minimizes this objective function. So if you remember, this w star is nothing but the, tell me.
Yeah, x times x transpose
Is
w
the
minus xy.
vector at which the gradient of this function becomes 0. Basically, this is the solution of your linear regression problem, right? Normal linear regression. Yes or no?
Yes,
Okay.
I
So
got
you
this.
know,
Like there was
so
some
this
sub part here.
subpart here. Okay, okay. I think there could be some subpart also. Okay, so no, there is only one part only. Okay, so there was only one part.
Oh, okay,
179
fine,
to
sir. Got
180.
it.
Okay.
Sir, that information is given to computers. Kya? D is equal to 3 and N is
Yeah,
equal
that is useless.
to.
Okay. Yeah, so next question. Okay. So now this question. Suppose we transform the data points in X, which is your data matrix, using this mapping. Assume there exists a kernel matrix K for mapping phi. Moreover, we categorize the model as parametric and non-parametric according to the following definition. So read this carefully. Parametrics Parametric models are those in which the samples in the training dataset, which we use to train the dataset, which we use to train to get the model, are not necessary for making the prediction. That is, after getting a model from this, we just throw away the dataset. So those are parametric. That is this, we got this parametric model. Okay, so this W which we get at the end is a parametric model, like in your cases of linear regression, ridge regression, all those we get a parametric model. While in, okay, now non-parametric, all the samples in the training set are necessary for making predictions in the test sample. So if you remember kernel regression, y prediction, this was equal to summation of 1 is equals to n I alpha I star. Then there used to be a kernel function x test comma xi, right? So xi were your data points from the training data set. So you couldn't throw away, right, the data set. So those types of models are known as parametric models. So kernel regression is a non-parametric model. Okay. So okay, so now you have to check what all is true about kernel regression. Okay, I think I have not added the options. Okay. So you have to check the options. The kernel regression is parametric. Is it parametric? No, because you need the training data set. So it's non-parametric, right? That is, at the end, you don't gain a parameter. You have to have the entire data set to make an active prediction. Is this part clear? So just remember, parametric means you have a model that is which has parameters in it which are used to scale the features. So kernel regression is parametric. That is not true because it is non-parametric. So second option is correct. Then kernel matrix is a semi-positive definite matrix. So that is true, right? So for kernel functions, there used to be two properties, which is symmetric and it should have a positive semi-definite matrix. Okay, so second option is correct. Third option is correct. In general, kernel regression is computationally expensive than simple linear regression.
Yes, sir. Because all time we need training data set.
Yeah, the thing is you need to calculate these dot products. Okay, you need to calculate these dot products for every test point. Okay, so this becomes very computationally expensive over the time. Okay, and those dot products are very, like, not small dimensional, so they are big. Okay, because your features could be like in tens of thousands, 10,000s, all that. Okay, so now this one, I think that okay, so I think those, that information regarding the first question was not useless, so it's used somewhere over in the third question. Okay, one more thing. So linear regression is parametric, kernel regression is non-parametric. What about k nearest neighbors? Is it parametric or non-parametric?
Non-parametrics.
Non-parametric, sir.
What about decision tree?
Parametric.
Parameter.
What about logistic regression?
I guess it's non.
No. In logistic regression, you also get a W. Okay. Then k nearest neighbor is non-parametric. Okay. Okay, fine. Now you have to do this. So the team modifies the relation as this: y is equals to x transpose w plus epsilon. Epsilon follows this distribution, which is Gaussian distribution with zero mean and sigma square as variance. Suppose sigma square is 1, d is equals to 3, and n is equals to 100. Assume that the summation of squared error is 0 for w is equals to w star. What is the negative log likelihood of the dataset at w star? Use logarithm to the base 10. Okay, so I'll give you 2 to 3 minutes. Try to solve this. Okay, then I'll do this. Okay.
Sir, can we do remaining question tomorrow because we are already past time?
I mean, see, I have to complete this. So I'll
Because
take for
even
half.
if you do, some may not understand.
See, it is getting recorded. So okay, let's do one thing. I'll take 5 minutes break. In the meantime, you can also rest. See, I'll be completing this anyway because I have to do this. Okay, let's see how
Better
much is.
don't give breaks, sir. Complete it, sir.
Okay, okay, fine. Okay. Okay, so anyway, I have to wait for 2 minutes because my throat is hurting from speaking continuously. So I'll just wait for 2 minutes. Okay. In the meanwhile, you can do this. Okay. So okay. Okay. So this is saying that so basically you have to see the probabilistic model of label generation given the data points. So this will be following which distribution? W transpose X, comma, sigma square, where sigma is 1. Okay. So now it is saying loss is 0. Okay. So it is saying loss is 0, right? That is y prediction is equals to y for each data points. So it is 0 for w is equals to w star. Fine. So I've written this. Now I've written this also. So now it is what it is asking, what is the negative log likelihood? So log of likelihood function of the data set at w star. So first you have to write the likelihood function, right? You can write that. Okay. So I've written this log. Am I audible or not?
Yes, sir. Audible, audible.
Okay. So I've written this log likelihood, which is product from 1 to n. That is for every data point. Then 1 upon square root of 2 pi sigma e raised to the power of minus W transpose xi minus yi square upon 2 sigma square. Okay. Then I have to take log of this. So this product will become summation. Then you have log of 1 by square root of 2 pi. Okay. So there is a product, right? This part, and this part. So log of AB is log of A plus log of B. So I have written it like this. So log of A plus log of B. So this part and this part and this part. Okay, so log of A plus log of B. So this is your log of likelihood function. So then when you, this is a constant, this whole term is constant. So when you add it n times, it will become n times of log 1 by square root of 2 pi sigma. Okay, then you have this part. Okay. So see, when you do summation of this term n times, this will happen, right? Log of E minus raised to the power minus W transpose x1 first data point minus y1 square upon 2 sigma square plus log of E minus this and so on. So can I write this entire thing? So you know that log of, just reverse of that, A plus log of B is log of AB, right? So this will become log of E, this part, this into this part, and then you have same base raised to the power same. So you know that 5 to the power 2 into 5 to the power 3, this is 5 power 5. Yes or no? So it will become log of E raised to the power minus of summation. So that this summation will come minus W transpose xi minus yi whole square upon 2 sigma square. Now why had they given us this information? To be used here. So I know that this term is 0. This entire term is 0. Is it clear? So log of likelihood function is this n times of this constant plus, okay, again, this power will come to the front. So this part is 0. Okay. So this part is 0. Now only this part is left. Now we had to calculate negative of log likelihood. So you have to take negative on both sides. Okay. Now you have to calculate this part. Again, they have said that base 10 should be there. So I did a mistake. So I took base E. Anyway, so minus n log of E 1 upon square root of 2 pi sigma. Okay, so this is left. Now I can write this as log of, so this is log A by B. So I can write it as log of E, 1 base E. So this will be 0 minus of this denominator. So this will become positive because there is a negative outside. So this is basically this. You have to, so this is the answer. Okay. Now the thing is, we had to calculate in base 10, but I did it in base 3. So I can just do this, right? So if you know, when you want to change base, so if you have log, suppose y by x, you want it in base E. So you can write it as log of E x upon log of E y. Okay. So this comes here and this comes here. Okay. So I have to change it to base 10. So I can change it afterwards. So I did the same thing. Okay. So now same thing has to be done here. Okay. So you'll calculate it and you'll get this 39.9. Is this part clear? Anyone, any doubt? Okay. Okay. So here you have to just calculate ratio of maximum likelihood estimate weight vector and the ridge weight vector. Okay, why is there a ratio? Because your weight vectors are just real numbers and not vectors actually. So W map is from R and W maximum likelihood, which is your W for the normal linear regression. Okay. So that is also for R. So you have to just calculate the ratio of it. So you know that W map, which is your ridge weight vector, it is equal to XX transpose plus lambda I pseudo inverse into XY. So they have given you X, they have given you Y. You have to first calculate this. So X, okay. Then this is your Emily, which is your linear regression weight vector. So first I have to calculate W map. So first I will calculate W linear. So X was given as this vector minus 2, 3, 4. The next transport would be a column vector. So I've written that down. Then WMLE is equals to XY. X is this vector. Then Y is your label vector. So this I have written. So if you calculate this, I'll get this. Now I have to calculate W map. So instead of writing this as a pseudo inverse, I can just bring it here. So this will become XX transpose plus lambda I. Okay, normal matrix. So now I know XX transpose was actually equal to 29 from here. So I've written 29 plus lambda I is 1. Okay. Lambda was given to be 3. So I've written this down here, 3. And XY, you have to calculate. We have already calculated, it was 180. So this would be 180 by 32. So you have to now calculate the ratio. So 180 by 29 upon 180 by 32, that would be 32 by 29, which is 1.103. So you can check the answer also. So 1.103. So 1.1 definitely lies in one between 1.05 and 1.20. Is this part clear?
Yes, sir.
Okay, so I'll do one thing. I'll just do some of the questions which need to be noted. Rest you can do it from your end. Okay. Okay, so L1 regularization. What is L1 regularization? What do you use in which norm do you use in L1 regularization? Is it corresponding to lasso?
Yes, sir.
Yes, sir.
Yes.
So L1 regularization reduces the risk of overfitting. L1 regularization tends to produce sparse model. Okay. Now L1 regularization always improves the model's predictive accuracy. No, because it might happen. See, when the features were redundant, then we wanted sparse models, right? To just avoid those avoid the importance of those redundant features, right? Then but if the features are not redundant, then it might happen that applying L1 regularization will reduce my model predictive accuracy because we took a wrong assumption on the data set. That is, features were actually not redundant. Is it clear? So L1 regularization not always improves the model predictive accuracy. We need to have certain information on the data like features being redundant so that we can apply it. Okay. So L1 regularization is primarily used to increase model complexity. No, because you know that the model which we get, which is the weight vector, it has lots of zero in it, right? It is a sparse model. So at the end, see what you will be using in as, so suppose this is your sparse vector. You can see there are lots of zero. So when you will be predicting, so suppose this is a general vector which you will be predicting. So x2 will be redundant, x4 is being redundant. So your model basically becomes a x1 plus c x3 plus uh, e x5 plus 6 f x6. So this is your model which you will be using. Okay, equation which you will be using for y prediction. While this would be much more complicated, a x1 plus b x2 plus c x3. So L1 regularization produces very simple models. Is it clear? It does not increase model complexity. Is this clear? Is this part clear?
Yes, sir. Yes.
Okay. Decision trees are supervised learning algorithm used for classifications. That is true. The k nearest neighbor algorithm is a lazy learner, which means it does not build an explicit model during training phase, right? It's a you know, you need to have the entire data set to make a prediction at the end. Okay, so you're not learning any model from it. So it's a lazy learner. Then in k nearest neighbor, the value of k represents the number of features used for classification. No, k is a hyperparameter which decides the number of nearest neighbors used in the decision, right? Is it clear? So this option is wrong. K nearest neighbor is a parametric model. No, it's a non-parametric model. So you need not read further. The depth of a tree is a hyperparameter and is typically chosen using cross validation. So that is true, right? Depth of depth of decision tree is a hyperparameter which is decided by the user, right? depending on the overfitting and all that. Is this part clear? Then this question, okay, we have already seen such questions, so same logic goes in this. Okay. Okay, then you can calculate the ridge regression weight vector beta. Okay, we have already done one example of this here. So we calculated this W, right? Okay.
Sir, you'll
Then
be sharing that PDF, right?
yeah. Okay. So now, okay, again entropy, you have to calculate all this. I think I have calculated somewhere. Okay, so I have calculated this entropy. Okay. Okay, so you have a data set of 500 loan applicants. You want to construct a decision tree to predict loan default. To determine the first split, you will use information gaze as the criteria. Okay, here is the distribution of loan default in the data set. So 150 applicants are defaulters, while 350 are not defaulters. Okay, non-defaulters. So you know that what is P? P is the, so you can take P as anything. You can take P as the fraction of defaulters, or you can take P as the fraction on non-defaulters, because your entropy function is, you know, symmetric. It will give the same answer in either case. Okay, so just take it as non-default, so that would be 350 by 500. So you'll get this. Then you have to get, you have this entropy formula. Just put the value, then you will get the answer. Okay, then okay, we have seen these types of questions already. Okay, so okay, so this is direct formula based question, I'll tell you. So okay, tell me what was the formula for binary features. Okay, binary features in generative story 2. So it was 2d plus 1 minus 1. Okay, so how many words are there? So vector contains 12 words, so d is 12. So you will get 2 to the power 13 minus 1. So 2 to the power 13 is 8192 minus 1, which is 8191. Is this part clear?
Yes, sir.
Okay. 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 Given a training data set with 100 data points, how many distances would you have to compute in the process of predicting level of a test point in k nearest neighbor with k is equals to 5? It's 100, right?
100
No matter
distances.
no matter what your k is, you always calculate all the distances to every point in the data set, and then according to the k, you pick the 5 or whatever is the k
Nearest.
number of minimum distances, and then you use the majority of it to get the predicted label, right? So it's 100, right? This is very trivial question, like I don't know why it is even there. Okay, so if the proportion of points belonging to class 1 in a node is p, for what value of p is the node entropy maximum? So you know that entropy function,
0.5.
yeah, entropy function is this, right? 0 1, and at p is equals to 1.1 by 2, it's maximum entropy.
Yes, sir. Yes.
Okay. Okay, then this question, we have already done this type of question, if you remember this. So basically, see, you have to use this. Yeah, so this question, this is exactly same as this question. It's just that here the data points are given as a matrix, but in this question the data points are given as a table. Okay, here, this is this part. So basically this is your one data point, this is your second data point, so you have to use the exact same thing. Is this part clear? Do you want me to do this? So it is already in the, I have done this in the, okay, so I have calculated all those parameters. Is this part clear? So there is nothing new. Okay, so this
Yes.
was your excess, then you had to calculate this, right? Decision function is, so you are getting this, right? Okay, so not much going in there. Okay, so I think we are done with this, both question papers. So any doubt anywhere?
No, sir.
Okay, so I hope you all were able to understand whatever was taught in this. Okay, okay. Yeah. So I'll just stop recording. Yeah. So any feedback you would like to give?